Thank you very much, Professor Liu, and good afternoon. Before we start, I would like to say thank you and express our appreciation that we could be here with you today, both to you, Professor Liu, and to Professor Deng, and also to Nina, who's somewhere. And Dr. Chen, also from our team, who have put in a lot of work in organizing this. So thank you very much. The preparations for this have taken us a while, and some considerations and some planning and some back and forth. The way we put this together is I have put a lot of the more fundamental things early on. For this reason, I will probably be talking a little bit more in the first half, but then in the second half, when things get a little bit more architectural, Candy will speak a little bit more. As you can see from our title in this talk, we want to give you an outline, and no more than an outline, of design cybernetics. And this is a field that people have worked in for a long time, for decades. The intersections between cybernetics, design, and architecture, that is a very rich field of practice and research and exploration. And there is no time for us to go into great depth. We would have to talk for a whole semester. So this is a brief contextualization and an outline, not more. And of course, it's just our perspective. And in the way we present this, it's going to be shaped a lot by our Western European, North American perspective. Yeah, there are different cybernetics and there are different designs in different parts of the world, and we cannot cover all of them. We try to stick to what we know. We will also go a little bit according to historical development. And to keep this manageable in terms of time, we are not really including any of our own design or our students' design, where we just go with something that might be considered textbook material if we only had cybernetics textbooks. But unfortunately, we don't have those. So let's get right into it. And let's talk about the term cybernetics. As many of you might know, the word cybernetics has its origins in an old Greek word for the helmsman, the person who controls the course of a ship. This is indicative of the fact that the field of cybernetics is about processes of control. And the word processes is at least as important as the word control in that sentence. Both fields, design and cybernetics, have in common that they are notoriously difficult to define. In neither field there is a generally agreed upon definition of what the field is actually about. There are many definitions of design, there are many definitions of cybernetics. We have picked two for the purposes of this presentation. The first one is a definition of design. Design happens when existing situations are changed into preferred ones. This is actually a rephrasing of something that Herbert Simon has written in The Sciences of the Artificial in 1969. And cybernetics happens when past performance is evaluated to guide future performance. So from these definitions, we already see that they are both interested in something that changes over time. And that's one of the major commonalities that makes these two fields compatible with each other. Most people, when they hear cybernetics, they think about control systems, control engineering, and technical processes. Design cybernetics goes a little bit beyond things like technical control and automation. And to some extent, we're actually interested in the opposite. We're using terminology that used to be applied to processes of control to processes that are sometimes out of control, deliberately out of control when people are creative. That's it basically in a nutshell. And both fields, design and cybernetics, have been explored and they have been practiced by human beings for a long time, since long before we had words for them and before we had academic institutions for them. And here you see two examples from China, the spoon compass and the south-pointing chariot, both of which are cybernetic in the sense that they can be used for navigation, but they're also design in the sense that they are products of creative innovation. To understand design cybernetics, we have to go back in time to the middle of the 20th century. even though, as I said, there's always a more ancient prehistory, but let's just start with the Second World War and the Cold War. That was a time when there were various technical and methodological developments that made people, especially in the Western countries, very confident in technical methodology. I've just put a few examples over here. The protection of convoys in transatlantic traffic, radar, radio proximity fuses in anti-aircraft artillery, that this was a very early feedback device, but also code breaking. Then the space age with the first satellite and the Sputnik shock put a big dent into this Western confidence in the power of methodology. And finally, the landing of humans on the moon being, in a way, a prototypical example of a goal-directed project. You may be aware of a famous speech that President John F. Kennedy gave to Congress, I think in 1961, when he said, before this decade is out, we want to put a man on the moon and return him safely back to the Earth. Very goal-oriented. A lot of these technologies have helped achieve goals, and that made people very confident in technology, in methodology, and rationality, the rational logic that underlies methodology, technology, and so forth. And with those developments came a great sense of optimism. So in the US and in other Western countries, industrial output was great, the economy was booming, and based on those technological advances from the Second World War and the space race, as I said, there was this huge faith in rationality, science, and engineering. And people thought those would basically be good to solve any kind of problem. If we just have the right technology, if we have the right methodology, we can solve anything. One problem that existed at that time was that these things had to be institutionalized. The idea of protecting convoys and how should those convoys be organized to minimize losses, there was a whole new field of research that formed around that was called operations research. People don't talk about that very much anymore, but it used to be a big and flourishing area of research, and both design and cybernetics came into existence as academic fields shortly after the Second World War, and much of that development grew out of operations research. With that, design and cybernetics were very young departments at universities. Think of all the other well-established natural sciences and the mathematics and so forth. They all had a long tradition. But now these new fields were formed as academic disciplines. The cyberneticians didn't really have a great challenge in playing along with the general academic way of working, but for designers that was challenging. Most design teachers from that era came from practice, and they did not work according to generally accepted academic standards and protocols. So the idea back then was that design is this young field and it is somehow deficient. They are not properly scientific yet, and they have to develop methodology, and then they will be like all the other departments and apply rational sort of scientific methodology. And that was what turned into the design methods movement. There was a big push to develop methods for design. And that started with a conference in 1962, and it lasted for about 10 years. There were four main characters behind the design methods movement. One is Horst Rittel, another one is Christopher Alexander, John Chris Jones, and Bruce Archer. And of course, a whole community around them. And they basically went about a task they set for themselves, which was to develop methods designers could apply, just as practitioners of other fields could apply their methods. Horst Rittel, many years later, looked back at that project and he says, the reasons for the emergence of methods in the late 50s and early 60s was the idea that the ways in which the large-scale NASA and military-type technological problems had been approached might profitably be transferred into civilian or other design areas. I think that in the beginning, outsiders from architecture, engineering, and business heard about the methods of the systems approach and thought that if it were possible to deal with such complicated things as the NASA programs, then why couldn't we deal with a simple thing like a house in the same way? Shouldn't we actually look at every building as a mission-oriented design project? So he's referring here to the systems approach, which is something that came out of the Air Force that basically broke technical projects down like a tree. We have a rocket that's supposed to go to the moon, let's say, and in order to do that, it has to fulfill 5 main functions. It has to be able to propel itself, it has to be able to communicate, it has to be able to sustain life. So we need subsystems for all of these functions. Then we take all of these subsystems and break them down into smaller and smaller subsystems. And once we've got all the little problems solved and we put all the solutions together, then the rocket as a whole will function. Why don't we take that systems approach and apply it to buildings and cities? That was the idea. I don't want to talk about the design methods movement too much, but I want to quickly give you an example of what that looks like. This is an example that was developed by Bruce Archer, and it's called the 229-step product design process checklist. We don't really have to get into all of the details of this, but let's just note that there are a lot of details. And it is basically a highly detailed prescription of the steps designers were expected to carry out. In this approach, rather than the designer making choices on behalf of users, the method author now makes choices on behalf of the designer, and the designer carries them out. Which basically means that the designer's responsibility and their care and they're familiar with the particularities of a given project are very likely to be overwritten by a script that was determined by someone else, somewhere else, outside of the context. And that did not go very well. And society as a whole didn't go very well. So by the 1960s and into the 1980s, various crises have changed the general atmosphere and this optimism that dominated the early post-war years. Developments like the Vietnam War, the escalating nuclear arms race between the East and the West, emerging ecological crisis, rising unemployment, all of that came together to lower the general confidence in what policy, industry, and science can accomplish in paving the path forward for society. This faith in rational methods and control gave way to an apprehension and to doubt, things like protest movements, and this physics-based conception of science that was based on forces gave way to a more biologically based conception of science that is based on interactions. And there was an emergence of a postmodernist movement that was explicitly against method. So within 10 years, the design methods movement came to an end, and it was rejected by the very 4 people who started it. And one of them we have here is Christopher Alexander. Later, he also reflected back and he said, there is a whole academic field that has grown up around the idea of leading exponents of these so-called design methods, i.e. those 4 people. I am very sorry that this happened, and I want to state publicly that I reject the whole idea of design methods as a subject of study, since I think that it is absurd to separate the study of designing from the practice of design. I have disassociated myself from the field of design methods. There is so little in what is called design methods that has anything useful to say about how to design buildings that I never even read the literature anymore. I would say forget it. Forget the whole thing. If you call it, it's a good idea to do, I like it very much. If you call it a method, I like it, but I'm beginning to be turned off. If you call it a methodology, I just don't want to talk about it. That was the end of the design methods movement around 1972, after 10 years. Was that the end of methods in design? You might ask, we have design methods today. Right, but the methods that we have today are no longer prescriptive, and they no longer claim rational academic rigor. Today, maybe in architecture schools not so much, but in product and industrial design schools, we very much use method collections like these, which are not really about step-by-step checklists for designers to carry out, but they are more enabling strategies to gain an understanding of a particular design challenge. Understanding the user, for example, understanding particular contexts. In here you have your affinity diagrams, things like extreme user interviews, you might have heard of that, rapid ethnography, cultural probes. There are long catalogs, but these are not really as prescriptive. And in architecture, you've got maybe similar collections that are about site analysis, concept development, massing development, things like that. These are methods we still use, but they are by no means as prescriptive, and they do not aim for or claim scientific rigor anymore. The relationship between design and academia in general, and academic research in general, has changed over the years. And I've got 4 snapshots here where we've basically got Herbert Simon, Bruce Archer, John Chris Jones, and then Ranulph Glanville. In 1969, Herbert Simon still argued strongly for design to become properly academic. Yeah, like all the other departments on the university campus, design seems to be deficient. They are not doing actual proper science. They need to develop rigorous standards and rational methods and become a proper science. And we've got changing pictures in between, but by 1999, Ranulph Glanville says, no, it should actually be the other way around. We should not constrain design within the standards of science. We should think of science and scientific research as a particularly formal version of the general human activity of design. The picture has changed a lot. And remember what I said earlier about design and cybernetics both being about change in time. When we look at the flow of time, we also have to recognize that science and design look into different directions. Science looks at what is there and describes it. Design looks forward and thinks about what should be. Yeah, and Herbert Simon actually put this into words, and he said, the natural sciences are concerned with how things are. Design, on the other hand, is concerned with how things ought to be. And between knowing what is and deciding what ought to be, there is potentially the is-ought fallacy, which occurs when a claim is made about what is ought to be based only on statements about what is. Taking stock of what is the case and then moving forward to determine what ought to be, in a way, it is what design and cybernetics are about. Remember what I said earlier about design happens when existing situations are changed into preferred ones. That's going from is to ought. Design happens when past performance is evaluated to guide future performance. That also is going from is to ought. But David Hume warns us that there's a potential mistake here. There's a fallacy that we can make. He warns us that what is alone is not enough to justify declarations of what ought to be in terms of formal rational logic, at least. What does that mean? To give you an example, we cannot say, based on rational reasoning alone, that because, let's say, residential buildings have always been net consumers of energy, therefore they always ought to be net consumers of energy. That is not a necessary conclusion. There seems to be something else that enters the equation. I'll give you another example. We could say humans have evolved to live on a plant and animal-based diet. Therefore, we ought to continue to eat meat. That is not a necessary, defensible logical conclusion. It becomes justifiable only if we realize that our values enter this line of reasoning. Our experiences, our perspectives, our desires, but just because something has been the case is not enough to determine how something should go on. If we want to get from past performance to understanding how we should guide future performance, then maybe the best place to look is rocket guidance, which is actually where much of cybernetics comes from. So I have a very, very old video here. I think this was filmed more than 100 years ago. The person that you see in this very grainy looking video is Robert Goddard. Goddard was an early American rocket researcher. But he is demonstrating in this series of films that he made how he implemented what we today call internal rocket guidance. The device that he holds in his hand over here is this contraption where you see that drawing over there. This is a spinning mass that is hinged on two axles, which provides an internal reference for attitudinal changes. We can watch this. He's demonstrating it first by holding up a bicycle wheel that doesn't do anything, but when it spins, you might be familiar with this. There is a momentum that can be gained by realigning this spinning wheel using the forces that also keep bicycles upright. Yeah? You've got a spinning mass and it wants to stay in its plane. And here he shows how a small version of this can be mounted on two free axes around a frame. And what we see here is the internals of, unfortunately the video quality is very poor, we see 4 fingers that can enter into the rocket exhaust at the end of a rocket to determine the direction in which the rocket thrust is deflected to steer the rocket. Now you see those fingers going into where the rocket exhaust will be. So here he's basically rotating the rocket in space inside the gyroscope, which is this spinning thing over there, is used as a sensor to guide how the rocket exhaust is deflected. This is an unsuccessful test where some wires were crossed in the wrong way. We've got positive feedback and the rocket just destroyed itself. Here we have another one where we see a successful launch. The contrast is really poor here, but if you look carefully, you see that it flies along an S-shaped curve, going back and forth. So whenever the rocket detects an error in its attitude, it basically corrects through negative feedback, which is basically what is visualized in the 2 diagrams on the right over here. We've got positive feedback, which amplifies deviations, and we've got negative feedback, which minimizes deviations. Generally, especially in technical systems, we're very interested in negative feedback because we design for stability and predictability. We want things to be stable and to correct themselves. Things like positive feedback are typically associated with things like escalating violence or pandemic spread or something like that. Those are examples of positive feedback. But negative feedback is something that we try to implement in various systems to make our world predictable and reliable. So here we've got Goddard again with a close-up picture of the gyroscope mounted inside his rocket, and the relationship between the steering mechanism of the rocket and the internal gyroscope is what we call a control loop. Whatever the gyroscope, the sensor, measures in terms of attitudinal deviations from where it's supposed to go is fed as a signal to, in this case, this would be the top view of a rocket that maybe has aerodynamic control surfaces, and they are deflected accordingly to correct the course of the rocket. This kind of negative feedback we have in all sorts of systems. Right now, I am standing under an AC control unit. Maybe somewhere in this room, there is a temperature-sensitive switch that monitors the temperature around us. If the temperature is getting too high, the machine starts up, cools down the room. When the temperature is low enough, it switches off, and there's also a control loop. I have built a mini version of this to show in the classroom. This is basically an old-style incandescent light bulb, and I've strapped a heat-sensitive switch to it, and I've also monitored its heat, and it gives us this very characteristic control curve. You could say that it is a system that tries to attain a goal. So with that, we've talked about process in time, we've talked about control, we've talked about feedback, but how to formalize that, how to conceptualize that so that we can talk about this in more formal terms, that we can write about it, that we can document it. From this question, I want to jump to Ross Ashby. In order to make processes of control amenable to formal description, he developed the notion of variety. Variety as a measure of the number of states a system can assume. And Ashby, I think since he was a high school student until his death, he wrote a journal. And the full journal is digitized and it's online. And there is this one moment that I have copied here. It says, I want to get away from the Shannon method of entropies. He's referring to Shannon's information theory that he developed to tackle cryptanalytical code-breaking problems. I want to move away from those infinite messages because I know in my control loop things are generally finite. I want something else. And he says, I want something I can count. So he invents variety. Variety basically means number of states a system can assume. Let me give you some examples. If you have a simple on-off switch, like this one, Ashby says it has a variety of 2, because it can have 2 states, on or off. If you have a dice for gambling, that has a variety of 6. It can land on one of 6 faces. If you have a keyboard, let's say a keyboard with 75 keys on it, you could say this has a variety of 75. Ashby describes this somewhat ambiguously. Sometimes he's counting variety like I just did, and sometimes he uses the log 2 of that number when he wants to represent this in binary. So instead of saying a variety of 75, he would say a variety of 7 bits is enough to count up to 75. There are also other complications in this. The more you think about it, you will realize that you have to be very careful here. If you think of the keyboard on your phone, it actually has a mode key where you can go from alphanumerics to punctuation, for example. Or you can flip it from English to Chinese. And you can flip it from English to Chinese to Russian. And all of a sudden, the variety can be huge. And how do you count that? How do you deal with shortcuts? You have to know what the system is that you look at. And based on that, you have to decide how to count variety, which basically means you as a subjective observer have to decide how you use this unit of measure. But there's something else. There is actually a difference between what he calls potential variety and actual variety. Think about the 3 bits of a traffic light. If you have 3 bits, the amber light, the red light, and the green light, these are 3 bits. There are 8 possible combinations. But in traffic control, we only use 4 of them, right? We only use the blue ones, the gray ones, the ones with the gray background, we don't use. You will not see a functioning traffic light that has all 3 bits on at the same time. So he calls this constraint. He says, when you take the potential variety of 3 bits and say minus constraint, what you then get is the actual variety. The variety that is actually being used within a particular control application. You can use that for something as simple as a thermostat, but you can also apply it to a mother and a child, the child having maybe a vocabulary of 3 words and the mother having a vocabulary of 30,000 words. You can compare them in terms of their communication and variety also in the human and in the social context. But there are challenges with this idea of variety. One of them is the difference between discrete and continuous signals. We could talk about the difference between the digital and the analog. To keep this very simple, I just show you these 2 music instruments. On a piano, we have discrete keys, which gives us a lot of control. Every time I hit C sharp, I get that frequency if the piano is tuned properly. And I have all of my notes. On a violin, the situation looks very different. The violin doesn't have markings on its neck. And between any two notes, there is a universe of frequencies that I can access. This makes it very difficult to compare these two worlds. Technologically, we can turn an analog signal into a digital, we can turn a digital signal into an analog with techniques like interpolation and quantization. That is possible. But conceptually, when we think about variety, it's still a very unresolved business for me. I wish someone could clean this up, but I fear it is impossible. For example, if you look at the piano, a standard piano, you would say, has a variety of 7 and a bit octaves. A standard violin has a variety of 4 and a bit octaves. I wouldn't say that the piano has more variety, because there is so much more nuance that you can get out of a violin, because you can get to all the frequencies between any of the two notes that are adjacent on the piano. So what is greater variety? Is it the bandwidth or is it the resolution? These are two different worlds that are conceptually difficult to bring together. But Ashby proposes variety for all of this. And we, as cyberneticians, we have to look at what we are dealing with. Should we count in binary? Should we count in in natural numbers? Should we consider this as a continuous bandwidth or as discrete states that are much easier to control and much easier to notate symbolically? We have to decide that. So let's change gear here for a moment and take a top-down view at cybernetics and its intellectual neighborhood. This table comes from a couple of papers published by Dent and Umpleby, where they compare different systems traditions, including cybernetics. There's also system dynamics, operations research that I mentioned earlier, general systems theory, and they compare these traditions in terms of their underlying assumptions. And these are all assumptions. We've got the traditions in the vertical columns, and we've got a couple of assumptions in the rows. And with all of these assumptions, these systems traditions depart and move away from conventional natural science, moving away from entities to consider the relationships between entities, for example. Moving from linear causality, A affects B, to circular causality, A affects B and B affects A. These are all conceptual deviations from natural science. When you compare all the systems traditions, you see that cybernetics is the one that departs from natural science the most. But it also, at the same time, approximates design the best. In acknowledging some of these assumptions, primarily the move from linear causality to circular causality, from determinism to indeterminism, and from not including the observer to including the observer. And those are aspects where design and cybernetics happen to overlap very strongly. So for the rest of this presentation, we want to focus on those. Departures from natural science where cybernetics and design depend on each other, reflect each other, and enable each other. Let's start this with a demonstration of the last one, including the observer. I already mentioned how Ashby encourages us to figure out our own definition of variety, depending on what we are working on. This is an example of acknowledging a subjective observer rather than defining something generally and objectively. Let me show you a few more examples to demonstrate what cyberneticians mean when they talk about acknowledging the observer and acknowledging observation as active participation. This is a video loop of the London Tube. And my question to you is, does the train come or does it go? Whatever it is, you can turn it around. Try to turn it around. There is nothing in what you're looking at that's changing. your attitude in observing shows that you are an active participant in what you're doing when you observe. And there are many optical illusions and demonstrations that can show this. I have some of my students know I have some priming exercise where I show the class a picture. Half of the class looks at one picture, half of the class looks at another picture, then they all look at another picture, and the two halves of the class are primed differently, have different previous experience, and see something different. There's a lot of that. This is a very famous example that comes out of a book from Ludwig Wittgenstein, which is an ambiguous drawing of something that could be seen as both a duck and a rabbit, depending on how we turn it. It's the same drawing, but you can look at it and you can decide it looks in one direction and it's a duck, or it looks in the other direction and it's a rabbit. We have to admit that when we look at this, we cannot look at this with what Donald Schoen calls seeing that. We are actually doing something else that he calls seeing as. I decide to see it as a duck. I decide to see it as a rabbit. Yeah, you could say in this example, we all see that there are stripes, but we can choose to see those stripes as the Mona Lisa. That's the difference between seeing as and seeing that. And all designers know this. A lot of our creativity comes from our very childlike capability to see things as. It's very natural for a child to look at the clouds and to see animals. And we have to professionally, as designers, recognize that what we see from our perspective may not necessarily what others see or what others appreciate. Like in this example, the client might say, I love it, but the end user maybe not so much. And with that come other questions about what is order, what is chaos, what is disorder. I've got a bunch of letters here, and the question to you is, what are we looking at? That's a trick question. It's very hard to know. We are looking at the alphabet in alphabetical order. So it looked chaotic until you know the key. So depending on what we know, we can make sense or not. Depending on what our personal conceptions of order and disorder are, can manifest itself in very different attitudes, for example, in our relationship to nature. So we have to acknowledge that the participating observer is a part of observed systems, and that includes designing. Nigel Cross has written a book where he talked about the loop in which designers engage with the world in terms of hackwork and magic. What he describes is very similar to what Ranulph Glanville describes as acting and understanding. This is where something very similar, but also very dissimilar to a control loop comes into design. As a designer, I engage with my surroundings by acting on it and then gaining an understanding of what happened. And this is a loop. And every part of this loop is equally important. We have to understand in order to act. That is what institutional education is about. First you get your license, then you get to practice. Understand in order to act. If you look at what babies do, it's mostly the opposite. They act in order to understand. And designers, in many cases, act in order to understand. But institutional education generally wants us to understand before we get to act. The interesting thing here is when we consider the hackwork part. Why is it called hackwork? Hackwork means we can observe it. A designer acting on the world, that is something a third person, an outsider, can see, oh, the designer is making a sketch. The designer is building a model. The designer is conducting an interview. All of the things we act are observable. But I cannot observe you being inspired, having an idea, or seeing as. Those activities are very private and they cannot easily be observed from the outside. And I just put this in here as a very small acknowledgement from a perspective of design research. If we want to research designers, we have to accept that there's actually a whole part of our practice that is not accessible to observation. And that's kind of the condition of empirical research, that we can observe things. But not everything we do as designers and not everything that's going on in our loops of acting and understanding is observable. So conducting empirical work on the design process is notoriously difficult. The design process, by definition, takes place in our heads, writes Brian Lawson. And Ernst von Glasersfeld says, I can never really know what goes on in somebody else's head. So let's get back to variety and how the term variety entered into design theory. For this, there are two people who are responsible. And they did this independently. They did not talk to each other when they did this. This one is Horst Rittel, the other one is Gordon Past. And both of these picked up a book written by Ross Ashby titled An Introduction to Cybernetics. And they stumbled across this measure of variety and they said, we need this in design. So Horst Rittel, very early on in his teaching, defined design as a process of generating variety and reducing variety, creating options and then making choices from those options. We also refer this to diverging and converging stages of the design process, which a bit more recently has been condensed into the so-called double diamond model of the UK Design Council. Maybe you know that. That's a famous design process model that basically reduces the design process to two diverging and two converging stages. Rittel didn't do that. Rittel was not interested in controlling or prescribing anything. He just wanted to appreciate that designers create options and reduce options. Pask wrote, this is one of the early parts where he picks up the notion of variety. The novel sub-theory, a sub-theory of design, is that structures may be designed to foster a productive and pleasurable dialogue. The dialogue is actually one of those loops. Later, Pask calls this conversation. This way of thinking is most clearly manifest in connection with the literary art forms, notably surrealism, which relies upon a variety, novelty producing juxtaposition of releases and supernormal stimuli. Pask uses a lot of words in his own way, but he's basically talking about some kind of productive and pleasurable dialogue that is based on novelty that can be described in terms of variety. So let's get back to Ashby and let's get back to one of the fundamental principles of cybernetics, that is Ashby's law of requisite variety. He says that when we have a control loop, and we have a controller and a control, like a switch and a light bulb, variety in both sides has to be in a particular relationship. He says, for effective control, the variety of the controlling system must be equal or greater than the variety in the controlled system. The controller cannot have less states than what it is trying to control. It has to have at least as many states as what it's trying to control. So in this example, the switch has two states, the lamp has two states, and those states can be mapped onto each other so that there is no ambiguity, no misunderstanding, and the system is in effective control. Going back to our musical example, you could say that the variety of the controller, if we think of the musician as the controller can reach everywhere. The controller has a lot of variety, but putting the fingers onto the neck of the violin is enough to control the instrument to play a tune. Same with our rocket guidance. The rocket can deflect from its intended trajectory around two axes. Let's say we have got a north-south and a west-east axis, and in the gyroscope we also measure deflection around two axes. So this is an example of continuous variety, violin rather than piano, but the variety of the controller matches the variety of the controlled. Glanville later says, no, we have to be even more precise about this. Because we are dealing with a loop, it is entirely symmetrical. Every loop must be entirely symmetrical if we want effective control. which basically means a violin player who can reach everywhere will not reach everywhere. The violin player will constrain himself or herself to only touch the neck. Otherwise, there would not be effective control. And now, maybe you would say, but Tom, I have seen different violin players doing very innovative things. Yeah? Maybe they flick their fingernail against the body of the violin to create some percussion sound. Exactly. When a musician comes up with that kind of move, they are out of control, they're innovating. And that's where we want to get. And that's why we are now interested in design cybernetics as a field that uses control terminology and principles and theories, but we are interested in applying them to processes that are not necessarily goal-seeking or in effective control. So it is important here to understand that variety is a quantity, but with this quantity comes quality. We are not design cybernetics, we are not really bean counting states very often. But there is a lot of recognition of fundamental qualities that we have to recognize when we're dealing with variety. Let me explain. This is Hans-Joachim Bremmermann, and he described the theoretical limit on computation in a self-contained system in the material universe. He's basically assuming that in a computer that has the size of planet Earth, where every atom could represent a bit during the whole history of planet Earth, that computer could not possibly process more than 10 to the power of 93 bits. Yeah, if you have any kind of computational problem that requires processing more than 10 to the power of 93 bits, you have to find another planet. Planet Earth couldn't do it even if you could turn the whole of Earth into a supercomputer where every atom can represent a bit. So that is a fundamental physical limitation where he says once you hit a computational demand of 10 to the power of 93, the problem is said to become transcomputational, can no longer be accomplished with the means of our planet. And this is where this becomes qualitative very quickly, because this number, 10 to the power of 93, can be reached very quickly if we think in terms of variety. And this was demonstrated by Ashby. Ashby has this idea of a field of 20 by 20 lamps that can be binary, on or off. He argues these 400 lamps have 2, because binary, to the power of 400, which is roughly 10 to the power of 120 possible images that they can display as a bitmap. If we wanted to separate all of these images into 2 groups, then the criteria for this selection would have to be selected out of a possible set of criteria of 10 to the power of 10 to the power of 120 possible selection criteria. And there are not enough atoms in the known universe to write this number in normal notation. Ashby says everything material stops at 10 to the power of 100. And this has implications in the stuff we do. For example, George Clear wrote in a paper about software testing. If you have a system of n variables, each of which can take k different states. Let's say, for example, you write a little script on your computer, and your script has 308 variables, but each variable can only be 1 or 0. If you wanted to test that program exhaustively, you couldn't do it with the means of our planet, because you're dealing already with a transcomputational problem, because your computational demand is greater than 10 to the power of 93. Or if you have only 93 variables, each of which can take 10 values, you cannot test this program exhaustively in terms of all the possible combinations. So we deal with this by simplifying our testing task. We are testing representative cases, or we are testing likely cases. We are not testing exhaustively. In design, Christopher Alexander comes up with another example. This was attributed to Christopher Alexander by Ranulph Glenville. I cannot find it in the literature. But according to Glenville, Alexander used this example. He said, materials can be formed by 10 to the power of 30 potential combinations of our chemical elements. A selection of any combination of 4 materials to design, for example, the interior of a room would be based on a choice of 1 among 10 to the power of 120 possible selection criteria. This number obviously far exceeds Ashby's limit to everything material. So the conclusion here is that, and Ashby says this in itself, the systems theorist may be defined as a person with resources not possibly exceeding 10 to the power of 100, but who faces problems and processes that go vastly beyond this size. What is he or she supposed to do? The systems theorist of the future, I suggest, must be an expert in how to simplify. And then he went on to simplify exactly what he just said. And he designs this device, which is the Ashby box, that has a vast internal variety. The user can flip the switch and the pattern of the 2 lamps going on and off will change every time you flip a switch, but you cannot predict how it's going to change. So that's a teaching device to show how little technology it takes, perfectly deterministic electromechanical technology, to completely go beyond what we can predict. Which from a technological viewpoint is terrifying, from a design point of view or from a playful point of view, it's really interesting. And think of other things that we use to play. When you think of dice, when you think of playing cards, when you think of the roulette table, these are all systems that are designed to create as much unpredictability and as much variety as possible with as little and as simple means as possible. So we can surprise ourselves. This machine has inspired the cybernetician Heinz von Förster a lot, and Heinz von Förster turned it into a diagram which he called the trivial machine is over here and the non-trivial machine is over there. The trivial machine has a very predictable input-output relationship. Every time you put in an A, out comes a B. Every time you input a B, out comes a C, and so forth. The non-trivial machine has an internal state, and the input, together with the internal state, determines the output. And every time it produces an output, the internal state goes to the next position, and there's a lot of position inside. That makes this system extremely difficult to predict. And the reason why Heinz von Förster is so interested in this technical device is because he says that we expect our technology, the technology that surrounds us, to be predictable and trivial. We want our systems to be designed to act as trivial machines. If a vending machine doesn't give us the soft drink that we selected, if we say we want to have a Snickers bar and out comes a Diet Coke, we get very angry because the machine has failed. It's not a trivial machine. That is a demand that we have on our technology that we also increasingly apply to each other. And Heinz von Förster emphasizes this in education, where he says, education is basically a system where we train young people who are unpredictable and surprising to become predictable and to offer known answers reliably with all the pain associated with that. And reliability and predictability and correct answers obviously have their place, but Heinz von Förster argues that this trivial machine image is now dominating how we treat each other and how we treat our children. As a response to that, there is now a whole bunch of cybernetic technology coming mainly out of architecture schools that tries to surprise us. Technology since the 1950s, 1960s that is not designed with the goal of being predictable, but with the goal of being delightful, or as Pask said, pleasurable, surprising and fun. And there's a history of those devices that I now want to ask Candy to present, and after that we'll proceed together.
It's not finished yet. I will introduce a few illustrations of what Tom has just introduced the theory for. Maybe you remember the fascination with non-triviality, with surprise, with, we call it today maybe innovation and creativity, and how we can get machines to maybe support us in this and maybe to play with us instead of being only controlled. Remember, in cybernetics, design cybernetics, we are not only thinking about control, we are also thinking about being out of control and how this can actually help and support us. Here we see a very early device by Gordon Pask. It's called Musicolor. It's one of the very first devices that he made. It doesn't look like very much, and it was not designed to be looked at. This is a device for music performances, and it can produce sound, and it can produce light. And it was put on stage not to control anything, but to be a participant in a music performance. So the system would listen to players who were playing music. Let's say they were playing jazz. And it would think about, oh, what's the frequency? What do I measure from the sound? And it would produce light and color in response. But remember, there's also human musicians, and they would also respond to the machine. The machine, again, reads what people are doing in terms of rhythm and sound, and you get a creative dialogue. So this is a machine that doesn't try to control, but it uses control to become a creative participant in a conversation. So this is an important step in our idea of what machines can do. This is a famous project that those of you in architecture may know. It's called the Fun Palace. And the Fun Palace was a very ambitious project. It's designed by Cedric Price. Cedric Price is an architect, but Cedric Price was talking to Gordon Pask and to many other people. For example, here, Joan Littlewood. Joan Littlewood was a theater producer. They were talking about the problems of society and how education was not doing what they were hoping to do. Remember, this was in the 1960s, as a period of great revolution in Europe, where the students were protesting and they were demanding for new models of education. So Cedric Price and Joan Littlewood proposed the Fun Palace as a place where everybody could get educated in their own way, according to fun. The principle of education was fun. And the architecture here mixes different principles. People could come into this building and build their own spaces, introducing responsiveness, but also introducing creativity. And the building had technology to respond to the people. The system had very early transmission of, let's say, video transmission from other places, or it had technology tracking what people were doing. This is about control in both directions. People control the building has feedback to the people, and both enter in a kind of a creative conversation. And the goal is to educate. Here is a slightly later follow-up by Gordon Pask. It's called the Colloquy of Mobiles. This system is the first installation where machines talk to machines as a creative dialogue. So you see here these very strange things. They are made to look a little bit like aliens, and they talk to each other. And these strange devices have different characters. Some are more like males, and some are more like females. And the males have a light beam looking for females. The females have a mirror, and the mirror can reflect the light back. And so they can enter into a conversation that is non-deterministic. So we don't really know what will happen. So they keep talking to each other, responding to each other, and people can join this conversation. So in this exhibition, people were given light flashlights, lamps, so they could also join in this conversation. This is a very interesting step. You had an autonomous machine system and people participating in it, but it's a process and it's non-deterministic, right? So here we are seeing machines used not for control, but using control to get out of control, to become creative. This continues this line of explorations in two more very interesting projects I want to introduce. That is the so-called generator project. As you see, it has to do with architecture. So you see here, actually, this is a model of physical elements on a site with a crane, but also it consists of a computer and a specially made board with digital units that can model and can control the plan for the building. So John and Julia Fraser, they thought about architecture not only as the final building. They thought about architecture as a process that does not end, a process where humans interact with the buildings. The buildings can interact with people, and you have, during the building process, but also during the design process, many degrees of freedom, and you don't have to stop at the physical form. And finally, this project, maybe you also have seen before. It's been done in the early 1990s at the AA in London by Julia and John Fraser together with students. It's called the Universal Constructor. The Universal Constructor is the most abstract of these models. It just says architecture is a logical state in space and time. With that, you can model anything. It is a universal, that's why Universal Constructor, the name. It's a universal model that you can use in the design process, for example. You can use it to model a building and to analyze a building. And you can also use it in the process to talk with your clients or your future users of the building. But you can also use it in order to control a reconfigurable building. This level of abstraction is very characteristic, and it allows you to think about architecture not only as a physical thing, but as a procedural thing, something that keeps adapting, something that keeps inspiring us, and something that allows us to have conversations. Speaking of conversation, I want to hand over again to Tom.
So what Gordon Pask originally, remember, called a productive and pleasurable dialogue, he later developed into what he calls conversation theory. And a conversation is basically something that humans can do in feedback loops with each other and with themselves. So we're now basically taking this idea of feedback, of output becoming input into a system, and we're taking it from a technical context and we're applying it in the human and in the social context. And of course, we're not necessarily, or we're typically not interested in a technical determinism, but we're still interested in processes of self-organization and feedback and so forth. So a lot of the technical principles still apply as metaphors in the human domain. Yeah, you can look at escalating interpersonal situations in terms of positive feedback. You can look at the opposite in terms of negative feedback. And we can be thought of as humans as being self-regulating systems. Obviously, on a biological level, we all self-regulate. My body right now controls my body temperature, but I'm also self-regulating my behavior. So if you would all look at me like you cannot hear my voice very well, I would probably move closer, regulate myself to get closer to the microphone. I have an effect on myself. That is circular causality. I can have an effect on myself. And that applies to various things in the social domain and in design. And to illustrate that, I have these two examples of what happens when we have feedback loops through which we can witness the consequences of our own action and thereby gain an opportunity to regulate ourselves. The first one is an industrial example. Imagine you have a factory that is located next to a river, and for its process, the factory needs water, maybe to cool something or maybe to clean something, but the water will get polluted in the process. Typically, that factory would tend to take in the water upstream and to release it downstream, to the detriment of everyone who lives downstream, because they now have to deal with the dirty water. If we could implement a regulation that requires such a factory to intake its water downstream and to release it upstream, now we have a loop where the factory becomes subject to the consequences of its own action, and now it is incentivized to keep its discharged water as clean as possible, because that's what it's going to take in. So that's an example of self-regulation. Another regulation of that kind is the type of aircraft seat, the passenger seat that you see in economy class on some airplanes, where when you recline the seat, you actually take up the leg space of the person behind you, which is not a very nice social situation. But there are other designs where instead of affecting the leg space of the person behind you, the lower part of your seat slides to the front and you recline by removing your own leg space. You are actually becoming more generous to the person behind you in reclining. You recline and the person behind you gets more space. That creates a much more desirable social situation, which basically means that by the way we set up the systems around us, we determine the degree to which we face the consequences of our own action and thereby gain an opportunity to regulate ourselves. Arguably, a lot of the systems that surround us, especially industrial production and waste removal, is hidden from us. Or animal farming and all of these things are hidden from us. We don't really see the consequences of our consumption behaviors very much. And thereby, we don't have much option to regulate ourselves in the way we probably might if we would see the consequences of our own action. So that means we are part of self-regulatory loops that can be quite a bit more complex than technical ones. So technical systems are typically single loop systems. In this case, we're looking at learning systems. A single loop in a technical system would just be your thermostat. Temperature feeds back, system controls itself. Single loop. In a double loop system, maybe I am involved. If the upper one over here, if that is my AC that goes just in a single loop, that's a very technical process. But now I can consider myself in a double loop process. And maybe at some point I switch the thermostat off and I decide to maybe not wear my business suit. Or I decide I don't need a heater in the winter. I just wear my jacket indoors because I don't want to burn so much fossil fuel. The outer loop now becomes an opportunity to consider the judgments underlying the inner loop. And there's a possibility for critical reflection and learning at higher levels. What Gordon Pask initially called a productive and pleasurable dialogue, eventually, as I said, he developed into conversation theory. So let's talk a little bit about conversation.
So conversation is quite important to design cybernetics. And I want to come down to describing that as a process and why we think it is a really important process to understand. It comes actually from conversare. In Latin, it means to turn together. So it's an activity where different involved parties do something together, right? So it's a process that is dynamic and it involves not only one person. So the image shows very clearly this is the movement of dancing together. You need to coordinate and you need to have an exchange in order to do that nicely and beautifully. Let's go through a scenario. Remember that Pask was talking about something that is productive but also pleasurable, and later he called it conversation theory. We need to understand this also maybe as a process of making meaning. How do we come to understand? How do we come to think new thoughts? I'm a design teacher. My job is to make students creative. And I use this a lot. And I have to understand, where do ideas come from? So it's a simple description, but maybe it teaches you something about the process of coordinating our understandings. So we start with this very simple situation, two people. And they're talking to each other. And the first one thinks this particular shape and speaks out the word tree, because for this person, these two things are connected. However, another person hears the word tree. Oh, but maybe he grew up somewhere different. Maybe he's not from Guangdong, maybe he's from Harbin. And the tree he understands in his mind has a different picture. But he goes, yes. So the way we can confirm is using different words, trying to describe. So he speaks it out again and says arbor, which is the Latin word for tree, trying to describe, find another word for what is in his mind. Remember, they cannot look into each other's mind. The other person hears arbor and in his mind has another tree. Slightly different, but still enough tree to think, maybe it's not exactly the same as what I said before, but maybe it's reasonably similar. Maybe it's reasonably close. So we say, yes, tree. But you can actually, from this exchange, understand that what is happening in both people's minds is negotiated. It's not the same. And we can actually work with this process of making meaning by fundamentally understanding that we are not trading particular meanings, we are negotiating them. We need to talk to each other to develop that. If I don't agree with my conversation partner, I could agree to disagree. I could say, I don't think we have a good understanding, but let's move on. That is also productive. But fundamentally, we are aware that our understandings are always different. Some people would say, maybe from engineering, would say, this is a problem. We are all different. That's a problem. We cannot really talk to each other. In design, I think this is our biggest strength. And the value of conversation theory is that we suddenly understand it's a source of something new. If we keep doing this, we come up with new ideas. So it's very productive. Instead of saying conversation is a transaction in one way, no, conversation is about coming up with a shared understanding by talking to each other. Here's Ranulph Glanville, who says, the meaning in a conversation is not a message that is transmitted and encoded. We are not computers. But it's what every participant makes of it. I speak what I can, you hear what you will, which you can repeat back to me in your words, so that I, listening, can make my understanding of what I take to be your understanding, of what you took to be my understanding. And then I can compare. So you see, this is a very interactive process, but also a very creative one, if we treat it like that. So error in this exchange is not a technical error. It always happens, and we could understand it as a very powerful source of new understanding. If you have several people joining in a conversation, it is inherently creative if we use it well. This is one of my personal heroes, Ernst von Glasersfeld. He is not a designer, but he wrote a lot about epistemology, and he is a radical constructivist. And he spoke many languages. He grew up in different countries, and he understood that language and the way people understand is completely different in each language. And we cannot make them the same. We are always translating, negotiating. And he says that these meanings have to be constructed. We are constructing our world by interacting with the world, interacting with each other. We are creating it. We are constructing it. So I feel this is very empowering for designers. We come back to Heinz von Förster, who says something very clear. It's the listener, not the speaker, who determines the meaning of an utterance. When I'm a teacher in the classroom, and I think I was very clear, I said the right words, but I know that every single person here in the room hears something different. And I cannot demand everybody to hear the same things, because you are all individuals. And this is something quite interesting and powerful to work with.
So that idea of conversation can be extended to design. The two talking heads, we can call them self and other. And self is always me when I talk about myself, but other can be many different things. Whatever I engage with in my loops of acting and understanding. I could engage with sketching paper and a pen. I could engage with another person, an imagined other person, with a piece of technology or with a physical model. And if I know how to listen, and if I know how to use mismatches of what I want and what the other responds with, if I know how to use that creatively, it will bring me to places that I didn't know existed when I started. And this is what I want when I design. Yeah, like when we have a conversation. Imagine you strike up a conversation with a stranger on a bus. You start the conversation on one topic, talk more and more and more, and after 5 minutes you talk about something you didn't really expect to talk about on that day. The conversation finds its own path into an area that you might not have expected, or that you might not have even known was something that people talk about. That's what I look for when I engage in a design process. How does this work? Number one, I must not impose control. I do not sketch, demanding of myself perfect shading, perfect 3-point perspectives. Instead, I just sketch whatever I sketch, and I allow the sketch to talk back to me. I'm sure many of you have seen a situation where you sketch something and maybe a week later you look at it from the side and you see something. I didn't intend to put it there, but it's a really good idea to see it as something else than I intended. This is where the seeing as comes back. So I have an effect on it, but it also is allowed to affect my thinking if I am open to listen to it. I could make a model, and it's so frustrating. The model keeps falling over. Maybe if it keeps falling over, the real building also wouldn't stand up. Maybe I should rethink my structure. Or maybe the colors don't come out the way I want, but maybe it's a better color the way it comes out. I have to be sensitive to unexpected things that happen, and that takes me to places I didn't expect. So what this means is now that, again, we are talking about loops, but these loops are not fulfilling Ashby's law of requisite variety. Yeah, remember, if you have effective control, the number of states in the controller, the number of the states in the control have to be exactly the same, no ambiguity. Maybe that's okay if I want to switch the light on and off. It's fine. There's nothing wrong about that. But in design, I want something else. I want to be out of control. Yeah, it's by definition that the variety I have and the variety another person has on a certain topic is different. This is why we have so many misunderstandings in design tutorials. And the key is to understand that those are not bad mistakes. They are productive errors that we can harness. I've got this over there, a conversation between two people. In this illustration, they have vastly different variety in their color vocabulary. So they will start to misunderstand each other. But maybe that can give them new ideas. This is the result of a survey of how people interpret different adjectives. Let's just pick one, this one over here. Not bad. And people were asked, like a large number of people was asked, where would you put that between 1 and 10 in terms of the worst possible, neutral, or the best? And then people took this survey, and you see how you get distributions that are essentially statistical. These words do not have objective meanings, but we have socially negotiated working understandings of how we should interpret them. But there is a lot of potential for every single word we use, for every single drawing we make, for every single model we make, to be misunderstood. So there's another example from a mobile chat. Honey, I will come home in 15 minutes. Can you make me a sandwich? There's a typo. Instead of sandwich, he wrote a sandwich. And then she said, okay, I did it. Here's your sandwich. Yeah, so instead of saying this is a mistake, we have to dismiss it or we have to correct it. Maybe that's an opportunity to do something interesting. And this is what we do as designers all the time. This is an example of a designer making a collapsible stool. And the idea was to look at a fastener early on in the process. I imagine the designer took a clamp to see what mechanism can be used to allow disassembling a stool. And then realized that the length of the clamp can actually act as a third leg. The clamp was initially introduced into this conversation as a tool, but it ended up as a piece of material in the product. It's a creative reconceptualization of what the clamp is and how it can be used. And we do that all the time. And in doing that, we allow not only our outputs that we design to change, in many cases, we even are just the questions we are trying to tackle. And we explain this with a metaphor from biology. And the metaphor is coevolution. You probably know Charles Darwin's theory of evolution, which states that biological species survive the more fit they are within an environment. Survival of the fittest. But Darwin, in the original version of the theory, he said the species evolved in an environment that is static, that doesn't change. But of course, this is not the case. The environment changes. For example, all the other species are also evolving. So we get circular interactions in evolution where we see one species and another species evolving together. Yeah, maybe one species realizes the other species is a good source of food. So the other species then evolves some kind of mechanism to defend itself or to hide. Yeah, and then maybe the first species develops some kind of way of avoiding that kind of defense, whatever. So there are circular relationships, and we can actually see that in these examples, that sometimes there are species that have evolved together. Flowers that work perfectly for the anatomy of specific insects or birds. And we use this as a metaphor to how we allow questions and answers, challenges and responses to change each other during the design process. This is very different from engineering. If you ask an engineer to design something, the engineer will ask you on day one, what is the specification and what are the performance criteria? And then they will carry it out, and at the end they will give you something that responds to that specification and to these performance criteria. A designer will come back and say, well, you wanted X, but actually doing my research, I now realize you should actually want a Y. So the question that is tackled is allowed to change during the process. Now, let's think of how little it takes to create a lot of variety. I was talking about dice. I was talking about playing cards. I was talking about the Ashby box. We can also talk about a very simple mechanical system like a triple pendulum. This is just a pendulum on a pendulum on a pendulum. And there is no model that allows us to predict this mechanical system. But it can surprise us and it can give us inputs that we may not have expected. And the trick is to use that surprise creatively. And there are so many examples of creative people doing that. These are just some examples of musicians. Alan Wilder of Depeche Mode is talking in this interview about how the band in the studio is sampling fire extinguishers, basically getting out of control and redefining what a music instrument might be. Victor Wooten, probably one of the best bass players who ever lived, produced a tutorial DVD called Groove Workshop or something like that. And in the interview on the DVD, he was asked, how do you come up with new stuff? He said, I don't try to do that at all. I just surrender control. I give my bass to a saxophone player and let them do something on an instrument they don't understand. Or I give it to a golf player who has no idea about bass playing, and I just watch what they do. And there will be surprise, and I just use that surprise. Jack White talks about making life difficult for himself as a performer. He says, to get from the microphone to the organ on stage for this particular song, I have time for 3 steps to be there in time. So I put the organ 4 steps away just to make it really difficult for myself. And then the ultimate surrender of control is John Cage, who composed this very famous piece titled 4 minutes 33 that has basically no notes, where you have the orchestra just sitting there for 3 movements, doing nothing, and the ambient noise that happens to be in the space is elevated to become the performance to be appreciated. Complete surrender of control and total openness to accepting whatever comes. What this means from a cybernetic perspective is that we are essentially looking at very different understandings of the word control. Ranulph Glanville says we have to distinguish constraining control, he also called it Hitler control, from the kind of control that skiers or surfers apply when they surf. Yeah, constraining control basically means making the other comply to our will, restraining, taking away ranges of movement, articulation. That is very different from the control of a surfer who maintains stability in the face of perturbation and the changing waves. And this kind of surfing control is basically at the heart of conversational cybernetic design processes that go back further in time than the history of cybernetics itself. The surrealists and the Dadaists, they had creativity methods, for example, that are very conversational. This is a method to create poetry that is based on cutting up a newspaper into different words, putting all the words into a bag, and then pulling words out by random and putting them on a piece of paper to create poetry. It's basically creation through abandoning control. Here's another one that was described by Ranulph Glanville. This is spell checker poetry. You can use a tool like Word and just type in garbage without looking, and it will give you all the red lines, and then you can right-click each word and see what the dictionary suggested you might have meant. And then just pick your favorite one from the suggestions and then use that to construct a poem. And he says that you can see a digital technology as, again, seeing as a tool where Microsoft Word just responds in linear causal fashion to my input. I press a button, the font changes to bold. But I can also see Microsoft Word not as a tool, but as a medium, as a partner in a conversation where, if I know how to listen, can be inspired to come up with something new. And that is a very interesting way of using digital technology in the creative process.
So again, playful ways to get out of control. We know many of them. This is a very interesting approach to take a child's drawing. A child is not completely in control, but to actually pretend that we just literally input that as a 3D model, and you get something quite creative because the child is not limited in their ideas, and also the drawing has a lot of ambiguity. This is a game we have been playing with students quite often. We call it in Chinese "ibi ibi." The idea is two people, each one has a pen, and we start with a random drawing, and the other player has to complement that drawing. So maybe I start with a curve. My conversation partner makes a mushroom out of it. I take the mushroom and make it into a rocket, and we keep talking to each other through the drawing. And you see here, this is how it might look like after half an hour, and it is extremely liberating. We use that as a kind of a design warm-up. We use it a lot with our children because it teaches you to make statements, but also to respect what the other person does. So it's a very equal, ongoing creative process. We sometimes also have processes where we don't fix meaning into things, but we are translating from one domain into the other. So here, for example, you see this looks like a defibrillator, a medical device. But actually, that's translated into a very playful toaster. The idea is that we don't stop at the boundaries of what's correct and what's incorrect, but we take the ideas into another domain and see what happens. And, many of these things maybe not so serious. Maybe you think these are child's play. These are silly ideas. But if we really want to get the new, we must play, and we must allow us to play. And maybe we play with our machines, and hopefully our machines can help us to play better. So in the process of conversation, Ranulph Glanville says, ideas grow and take on their own life, developing and changing in a manner that is essentially unpredictable, and which increases in variety, richness, and depth. So if we respect the creative process, if we understand about being in control, but maybe also going out of control, also in conversation with our machines, we can get a much richer experience for us all. And I would like to just summarize a few things about design cybernetics. Maybe this is the takeaway after this very long lecture that allows you to understand the history and the principles. Design cybernetics recognizes and really builds on circular causality, right? Conversational processes. It recognizes that meanings are built up subjectively. They're constructed. The world for us is constructed, not found. In that we are different from rationalist science. And there's value in the error, in the noise, in the misunderstanding. We understand that this is actually very much a part of what we want. We want to work with the controlled and the out of control. And conversation can be limited by too much control, linear control, deterministic control. We also don't want to always insist on objectivity because we are humans. And always only exercising deterministic control may not capture what we need. Because deterministic control means to keep the path. If we want the new, if we want creativity, if we want our world to change and adapt, we have to look into playfulness, engaging with a world where new things are allowed to happen. And that's the end. Thank you very much.